All right, guys. So now we'll move on to chapter 6, statics of rigid bodies. Okay, so when it comes to rigid bodies in equilibrium, okay, so you have had some sort of an introduction on this in M2 mechanics 2, right? So this first part is about involving about rigid bodies which are suspended in equilibrium. So do you recall the theory? So basically, the theory when it comes to suspending object, any object is that what the point that you suspend and the center of mass is always going to form the vertical, right? Do you recall this theory? So if you don't, let's kind of go through examples and let's kind of refresh our memory. Okay, so they say here if a body is resting in equilibrium, okay, so we'll first go on here. Okay, if a body is resting in equilibrium, because they're talking about resting in equilibrium, okay, not about the suspending part here. If a body is resting in equilibrium, then there is zero resultant force in any direction. That is obvious, right? If it is resting in equilibrium, there is no resultant force. This means that the sum of the components of all force in any direction is zero. This is M1, guys. This is M1. If the object is completely in equilibrium, that means the sum of components is zero to any side. Okay. And the sum of moment of the forces about any point is zero. Guys, this is M1. Okay. This is an M1 section. You know about this. If an object is in equilibrium, the resultant force to any direction is zero, and the sum of moments, clockwise or anti-clockwise, it's going to be zero. Okay, that's M1. Okay, so this one, when a lamina is suspended freely from a point, or when it pivots freely about a horizontal axis, it will rest in equilibrium in a vertical plane with its center of mass vertically below the point of suspension or the pivot. So this is the M2 section. This is what I was talking about. Okay, so what's the theory? So if you have an object, okay, so if you have an object and you are, let's say this is the center, I'm just taking a 2D object to make things easier. A, B, C, D. Okay, and if you are, this is the center of mass, and if you suspend from the point A, so the point A is where you suspend. So what's going to happen? The object will tilt in such a way so that AG becomes the vertical. The line AG becomes the vertical. Basically, I mean, you don't always need to draw. Now over here, you can see in this case, they have drawn the cylinder. So in this case of the cylinder, okay, so this is the cylinder. I'll just draw it in a horizontal look. Okay, so this is the center of mass of the cylinder is exactly in the middle. So let's say this is the point A. So they are suspending the cylinder from point A. That means you have it from point A and you hang it. So what's happening? The rule is always the point that you suspend and the center of mass will become the vertical. So what's happening here is, guys, in can you see? So over here they have drawn how it looks after it has turned. So you suspend from point A and this will turn. And it turns in such a way that AG becomes the downward vertical. Okay, so you really don't need to be concerned in drawing this diagram, because drawing this requires you to visualize this in your head, right, to see how it looks after it turns. So you have to take this and you have to turn it. Okay, so that's really not required. All you need to know is, I mean, whatever the way the diagram is there, you need to be able to you just need to draw the line and construct the vertical on your own. Okay, so this is more than enough. Okay, so you don't need to draw the one that looks after it has been turned. If you can draw it, that's good. But it's not technically required. Okay, because it will take some of your time to draw this. You understand? This diagram is what they've drawn over here when it has turned. Can you all understand? So when it actually suspends, this AG is the vertical. Can you see? Okay, so we don't need to go for that. So okay, so they are saying here this result is also true for a rigid body. This particular result, that's the cylinder. Okay, so for a 3D object. Okay, and then they say when a rigid body is suspended freely from a fixed point and rests in equilibrium, then its center of mass is vertically below the point of suspension. So this is the M3 part. Okay, so this is the new part. Okay, because in M2 you learned about laminas. Okay, so in M2 we were dealing with laminas, but now in M3 you deal with rigid bodies. Okay, so you never had that in M2. Okay, guys, so this is the M3 part. So let's quickly go through this simple example. Okay, so I'll go through this example as well to give you an idea before we move on to the exercise. A uniform solid hemisphere has radius r. It is suspended by a string attached to a point A on the rim of its base. Find the angle between the axis of the hemisphere and the downward vertical when the hemisphere is in equilibrium. So honestly, you really don't need to go draw this diagram because drawing this is really challenging. Okay, but if you can draw it, that's perfectly fine. So what you can do here is, one of the easy things to do here is you draw the normal hemisphere that you usually draw. You draw the axis of symmetry. This is the point X they have marked, right? So you know the center of mass is at a distance 3r/8, right, guys? The center of mass is at a distance 3r/8 below X. Okay, and they're hanging this from this point A. Are you with me? So all you have to do here is, okay, all you have to do here is from point A, you construct this line. Can you guys see what I've done? So this line that you draw here, this is the vertical. Okay, so that's all you need to do. So they're asking you find the angle between the axis of the hemisphere. Okay, so axis of the hemisphere is this one. Okay, you know this is the axis of the hemisphere. Okay, so axis of the hemisphere and the downward vertical. So this is the downward vertical. So where do they meet? Axis of the hemisphere and the downward vertical. So the angle between them is this theta. Can you see? To find the angle between the axis of the hemisphere and the vertical. This is the angle theta that they're asking you to find. Okay. So you're supposed to find that angle. Okay, so all to find this angle, guys, it's really easy. You can consider, can you see there's a right angle triangle over here? There's a 90-degree over here. And you basically have a right angle triangle. Okay, so this distance is, the radius is r. Right, guys? So radius is r. You can go for what? What theta? Sine theta is opposite over hypotenuse. Cos is adjacent over hypotenuse. We can go for tan theta. Are you with me? Tan theta is opposite over adjacent. So tan theta is 8/3, guys, and you can do tan inverse of 8/3. So tan inverse 8/3 and give your answer in degree mode. So that's the answer they have given here, 69.4 degrees. That's correct. 3 years. All right, guys. So you don't necessarily have to draw the tilted diagram, okay, because it's more challenging to draw that, but this one is quite easy to draw and to understand. So it's sufficient to draw this. All right, guys. Okay, so that's the an easy explanation. Another way to explain the example. Okay, guys. Okay, guys, we'll move on to exercise 6A, question number 1. A uniform solid right circular cone is suspended by a string attached to a point on the rim of its base. Given that the radius of the base is 5 centimeter and the height of the cone is 8 centimeters, find the angle between the vertical and the axis of cone when it is in equilibrium. So guys, just draw the cylinder. Okay, it doesn't matter whether you draw it horizontally or vertically. Okay, so whichever way, just draw the cylinder. Sorry, it's a cone. Okay, not a cylinder. Okay, it's right circular cone. Okay, so this is the axis of symmetry. Okay, a uniform solid right circular cone is suspended by a string attached to a point on the rim of its base. So when you consider the rim, guys, in the sense of the diagram, consider the rim over here. It's easier for you, okay? Because any point that you consider, I mean, it's the same look. The thing is that, to construct the triangle, the rim, consider the rim at the edge of your diagram, okay? Given that the radius of the base is 5, so this is 5 centimeters. And the height of the cone is 8 centimeters. And the height of the cone is 8 centimeters. Find the angle between the vertical and the axis of the cone when it is in equilibrium. Basically, they are suspending it from here, right? So this is the point where you're suspending. So when you suspend it from here, they are asking you to find the angle between the vertical and the axis of the cone. So guys, you know this is the axis of the cone, right? So this is the axis of cone. Okay, so guys, center of mass G. Center of mass G, do you recall? Center of mass, so let's say this is the point O. OG is your Y bar, right? And that's at a distance, 3h over 4 from the vertex, h over 4 from the circular face. Am I correct? Okay, guys, so it's at a distance h over 4 from the circular face. So h is 8. 8 over 4 in the sense it's going to be 2 centimeters. So guys, construct the vertical. So the vertical is going to be from the point that you suspend and this G. Okay, so this is the vertical. The green color line is the downward vertical. So when you consider the downward vertical, guys, considering the downward vertical, they want you to find the angle between the vertical and the axis of the cone. So can you see? So you need to first of all identify the angle. So this is the angle between the vertical and the axis of the cone. So you're supposed to get this angle. How do you get this angle? Construct a right angle triangle. And you can see you can construct a right angle triangle in this manner. Are you guys with me? So it's easy now. So we know the distance. This is 5 centimeters. OG distance, we just found out that it is 2 centimeters because that's our Y bar. Right? Do you agree? That's our Y bar. All right. So guys, tan theta, right? So it should be tan theta, opposite over adjacent. Opposite is 5, adjacent is 2. And guys, get tan inverse and get me the answer 3SF. So tan inverse of 5 over 2. All right, guys. So the answer is 68.2 degrees. That's in degree mode, correct to 3 significant figures. Okay. Okay, guys. So moving on to question number 6. A solid is formed by removing a solid hemisphere of diameter 6 centimeter and center O from a solid unit right circular cylinder of height 10 centimeters. Guys, can you see? So actually before you can see there's a cylinder here and they are removing a hemisphere and the hemisphere is removed on the axis, right? It's symmetric the way they have removed it. Okay. The cylinder is suspended by 2 light inextensible strings which hang vertically. The strings are attached to points capital A and B on the rims of the solid such that AB is parallel to the axis of the cylinder. The solid has a density of 1 over 5 kilogram per cubic meter. This should be kilogram per cubic meter and hangs in equilibrium with AB horizontal. Find the tensions in the string. Okay, guys. So before we actually think about finding the tensions in the string, the first thing you need to do here, the first thing we have to do here is we need to locate the position of our center of mass. Okay, we need to locate the position of our center of mass. So first, let's consider the object. So object, mass, and center of mass. Object, mass, and center of mass. So when you consider that, the object, okay, so first we will consider the cylinder. Okay, so the mass, so the mass of this guy is cylinder. So it's pi r square h, right? Pi r square h, and then the density, the rho is given to you. Can you guys see? So this is the rho value. Okay, so the rho value is 1 over 5 kilograms per cubic meter. So guys, this is a little bit concerning over here. Now you need to be a little bit cautious because the unit here is in, they have given this in cubic meters, right? And we have here all our units in centimeters. So actually we are getting cubic centimeter. When you multiply pi r squared, we get cubic centimeters. Is that correct, guys? Okay, let me check on this. Okay, so guys, over here, what we'll do here is that's actually the density. Actually, it will cancel out, right? So if you use, I'll go with rho for now, okay? Because it's kilogram per cubic meter. Okay, so let me go with the normal, kilogram per cubic centimeter rho, because the thing is at the end of the day, it cancels out. And it's going to change all our units to cubic meter. Right now, it's going to be so time consuming, right? And anyway, end of the day, since the rows cancel out, so we really don't need to take too much time onto that. Okay, so let's just go with rho. It cancels out. Okay, so there's no need to change all our units. So I get here pi radius square. The radius of the thing is 5 centimeters, right? And the height is 10 centimeters. So into rho. So we get here 250 pi rho. Right, guys? And then the center of mass is at a distance so from the point O, considering from point O, it's you can see it's symmetric. So we only have the x distance needs to be considered. Y bar will be 0. Okay, because we have an axis of symmetry. So x distance is going to be at 5 centimeters. Do you agree, guys? Okay, and then let's go for the next one. So the next object is you're removing the hemisphere, right, guys? So you're removing a hemisphere. The center is at O. So the volume half of 4/3 pi r cube into rho. And what about the radius? The radius is 3 centimeters, right, guys? So half of 4/3 is 2/3 pi radius cube. Radius is 6 divided by 2, that's 3 cube into rho, right, guys? So that's going to be 3 cancels, 3 and 3. So that's 9 times 2, 18. 18 pi rho. Right, guys? Do you agree? So 18 pi rho, and the center of mass of the hemisphere is going to be at a distance 3r/8 from O, right? So 3r/8. So radius is going to be 3 centimeters. So 3 times 3, 9, 9/8. Do you agree, guys? Okay, so for the final object, so our final object is going to be the two of them combined together. Okay, so you're removing, right? So the mass should be subtracted. Can I know the mass? Okay, guys. So that's 232 when you subtract, okay, because you're removing masses. So remember, you should subtract. Okay, so let's quickly get that 250 pi rho into 5. You're subtracting with 18 pi rho into 9/8 equals 232 pi rho into x bar, right, guys? So pi rho is common with everyone, and that should cancel out. Can I know the x bar answer? All right, guys, can you see? So it's 5.30. This comes in centimeters because we measured our center of mass in centimeters. Okay, so because these distances are in centimeters, your x bar will also come in centimeters. Okay, so correct the previous step. That's your x bar. Okay, the exact answer is 4918/928, but 5.30064, it goes on like that. Okay, so 3 is at 5.30. Okay, that's my x bar. But however, it's not the X bar that they require here, right? So for 10 marks, they are asking you to find the tensions in the string. Okay, guys. So now they are saying this particular object, they are suspending it. Can you see? Okay, so they are suspending this object, and your task is to find the tension. Okay, so let's mark everything on the diagram. It's actually really easy. Okay, guys. So let's get the tension here. So now we know that the center of mass. Okay, so let's say it's over here. Okay, so we know that this distance is the 5.30 centimeters, right, guys? Okay. Okay, they are asking you to find, now you know the center of mass is the place where the weight of this particular object is acting, right, guys? So you know it's the center of mass, it's the place where the weight of this particular object is acting. Do you agree with me? Okay, so let's use the weight as mg. All right, guys. So let's use the weight as mg. And now your task is to find T1, T2, T1 and T2. Okay, so this is actually M1. Okay, or you can even consider M2 moment here. All right, so all you have to do here is, you know, the object is in equilibrium. So you can go for vertical equilibrium here. So when you consider vertical equilibrium, okay, so T1 plus T2 is equal to capital Mg. Right, guys? So that's one equation. Okay, so that's one equation. And the other equation, you can consider moments around A. You can consider moments around A. Okay. So considering moments around A, you know the rule. When you consider moments around A, the that particular person is not included in the moment, right? Okay, so let's consider moments around A, guys. When you consider moments around A, you only have to concern with other forces. So over here, we have the mg force. Can you see? So we need to consider the effect of mg. Okay, so mg is acting in this downward direction. Can you see? So the line of action, I've drawn it upwards. So considering from point A, guys, can you see from point A, mg provides a clockwise moment. Can you see? So mg provides a clockwise moment, and the distance is 5.30. Do you agree? So mg gives a clockwise moment, and the perpendicular distance is the 5.30. And if you consider T2, T2 gives a anti-clockwise moment. Can you see from point A, T2 pulls upward. So it provides the anti-clockwise moment. Therefore, minus T2, and the distance, guys, from point A, the perpendicular distance is 10 centimeters. Can you see? So this is equal to 0. Why? Because if the object is in equilibrium, the sum of moments must be 0. And guys, let's make T2 the subject. So mg into 5.30. Shall we use the exact figure? mg into 5.30 was 4918 over 928. Okay, let's go for 3SF afterwards. Okay, so let's use, otherwise we are doing 3SF and another 3SF, so it rounds off a lot. Okay, so this is 10T2. Okay, so now guys, we have to get the mass, okay, and then divide and then input the 10 here. So how do we get the mass? Okay, guys, so now to get the weight of this object, you can see I have the weight here, 232 pi rho, okay, but the thing is this, okay, so now this is the place where we are going to consider this, the rho value, 1 over pi kilogram per cubic meter. Now the thing is, guys, over here, the radius, height, we've been using it all in centimeters. So remember, we have all these units in centimeters here. Okay, so 232 cubic centimeters is what we have our units here, because all of these are in cubic centimeters. Okay. Now the previously I did not consider much of this row because it cancelled out. So it did not make us any effect. Okay. But now you need to understand 232 pi is in cubic centimeters, because you have been measuring the R cube, everything in centimeters. But rho is 1 over pi kilogram per cubic meter. How did I get this value? 1 over pi kilogram per cubic meter. I got it from the question because it's given. A solid has a density of 1 over pi kilogram per cubic meter. This is given in the question. And this is not me, but it's given in the question. So I'm using the fact from the question. So then, guys, another thing is, here we have cubic centimeter, here we have cubic meter. The units do not match, so we need to fix it, right? So how do we fix it? centimeter to meter, you know, it's multiplying by 10 to the power minus 2. Basically, divide by 100. Divide by 100 is 10 to the power minus 2. So when you do it 3 times cubic, that's going to be divide by 10 to the power 6 or multiply by 10 to the power minus 6. So these are basic conversions. Okay, converting cubic centimeter to cubic meter, you have to just divide by 10 to the power 6, or in other words, multiply by 10 to the power minus. All right, guys. So 1 over pi kilogram per cubic meter, guys. So then this cancels. The cubic meter part cancels, and you now get the answer in kilograms. Can you see? So your weight, the mass, total mass is gonna be 232 into 10 to the power minus 6 kilograms. All right, guys, are you with me? So we have our total mass. Shall we use that value here? So M is 232 into 10 to the power minus 6 kilograms. G is 9.8. This is 4918 over 928. And here we have 1 over 10. The 1 over 10 is 10 came down as a division. Okay, so can I know the answer? Okay, then guys, okay, I have a question here regarding now you're asking me about the centimeter. You're saying the 5.30 is here in centimeters, right? But over here, the 10 is also in centimeters, right, guys? So actually, if you see here, this 5.30 is the 4918 over 928. That's the centimeter one you're talking about, right? And here the 10 is also in centimeters. So actually, it cancels out the centimeters. So even if you want to be safe, you can convert this to meters. Actually, what by dividing by 100, right? Or by multiplying by 10 to the power minus 2, and you can see when you bring them to one side, they all cancel out. Okay. So it doesn't make any effect, but you know, to be safe, you could convert them to meters as well. Okay, since everything is in SI units now. So anyway, but we'll be getting, we are trying to, yeah, we're getting tension now. So the tension will be in newtons. So it comes, this is in kilograms. Yeah. So the centimeters have cut off. So what's the answer?
Don't.
All right, guys. So it's 1.2049 into 10 to the power minus 3. Corrected previous step. That's going to be 1.20 into 10 to the power minus 3 newtons. That's done, guys. And to get T1, they want both tensions, right? You can use the equilibrium equation. Okay, so T1 will be mg minus the T2. Okay, so you can use the full figure here, 1.2049 when you are doing the subtraction. Or you can use extra figures. Okay, so M value we found. M was 232 into 10 to the power minus 6 into 9.8. 1.2049 into 10 to the power minus 3. All right, guys. So what's the T1 value? Okay, so that's going to be 1.07 into 10 to the power minus 3 newtons. These are all written correctly 3 years. Okay. Right, guys. So this is, I hope this is clear. Okay. So that's how we do that question. And then moving on to the next part. So 3 marks. Part B. The string at B breaks and the solid hangs in equilibrium from point A. Find the angle between the circular plane face and the solid and the vertical. So I believe that's really easy, right? So when the string at B breaks, that's just a normal question now. So there's no string here. Okay, so you know the center of mass is over here. And immediately, if you're suspending from one string, you know the rule, right? The point that you're suspending and this G becomes the vertical. So this is the downward vertical. Okay, so that's 3 marks. You can see it has a relatively less amount of work. The string at B breaks and the solid hangs in equilibrium from point A. Find the angle between the circular plane face of the solid and the vertical. So circular plane face is this one. Guys, can you see? So this is the circular plane face, and the solid, guys, the angle they are asking you is for this one, right? Can you see? This is the angle they are asking, right? Can you see? So this is the vertical and this is the circular plane face. They are asking for that angle. So can't you find that? You already know this is the x bar and you know that this is the radius, right, guys? That's quite easy. So tan theta, opposite over adjacent, opposite is the x bar, adjacent is the radius. So x bar was 4918 over 928 or the 5.30 divided by radius of the thing is 10 centimeters diameter. So radius is 5. So guys, Let's get the answer. How much is it? Tan inverse. Get the answer. 3SF. Right, guys. So it's going to be 46.7 degrees correct to 3SF. Okay, so tan inverse and get the answer. Right, guys. I hope you understood this part, right? Angle between the circular plane phase and the vertical. So this was really a very normal sum. So this was the one where you had used a little bit of technique. The 10-mark question, but it's really I hope you understood my explanation. Right, guys? So yeah. Okay, so this is the end of the question.